Muravio, who is a senior lecturer in business and management in the School of Business Law and Social Sciences at Abertay University in Dundee, Scotland. And Dr. Muravio has a lot of experience in the UK, 7 years of teaching there and researching. In the US, 7 years, Kazakhstan and Central Asia, more than 12 years. And his research profile is in public-private partnership, energy policy and governance, and social entrepreneurship. Dr. Muravio, you have a very rich publication record of 7 books, 5 monographs among them, and more than 50 journal papers. If you would like to add something to my introduction, please feel free to add it.
Okay, thank you very much. So let me begin straight away. Good morning, everyone. So I want to speak today about a new model of energy security. So in this conference, we heard this term quite often. Energy security was noted in quite a few presentations. Let me show you my aims. One, I want to show the need to reconceptualize the energy security models by showing some limitations. And also I want to sketch some features of a new model. And of course, I would welcome your feedback. I want to know that this is a conceptual paper rather than the paper that draws on the particular data set or interviews. So let me show my outline. So I want to start with pointing to the typical approaches to energy security as of today. Then I will speak about their limitations. I will then proceed to the theory that would underpin a novel energy security concept, and then we'll highlight its core, show implications for policy and governance. Then we'll speak about the links between a new energy security model and net zero, and we'll conclude. So let me begin with the typical approaches to energy security as of today. There are quite a few. In fact, I just noted that in this conference, we heard many speakers talking about energy security or using these words in their presentations. And in fact, it looked like we all agree on the meaning of energy security, which is not true. There are quite a few concepts and they vary. This is on the left-hand side, you can see one of the typical approaches to energy security. It has the title of 4 A's, letter A's, beginning with availability. And the focus is generally on the availability of energy sources and energy. It has other dimensions such as accessibility, affordability, and others. So, but the main thing, of course, is availability of energy. On the right-hand side, there is another set of approaches, but again, it focuses on the energy supply. So, to summarize, and of course, this is a very brief talk about the existing approaches to energy security, but the summary tells me that energy security is viewed as the security of supply. Security of supply. There is the clear overlap between what you can see on the left-hand side and on the right-hand side. Commodity supply continuity, the word continuity is used on the right-hand side. On the left-hand side, we see availability, which has the obvious overlap. So while I acknowledge that the concepts are different, there is the commonality between them, and that is the focus on security on supply. As of today, this is the prevailing perspective among most academics. However, I want to say that this perspective fails to explain the recent and, in fact, ongoing energy crisis in Europe in particular and in other parts of the world. As we know, there are rapidly rising energy prices. In the UK, for end consumers, for individual consumers like myself, the expectation is that the prices for natural gas will rise, will become 3 times as much, possibly 4 times as much during 1 year. So I don't really know how that corresponds to the security of supply. Yes, supply is there, but at the price that many people will not be able to afford, or they will have to choose between supply of energy and, for example, food. So what is secure there? Also, we know that Europe, including the UK, experiences the lack of natural gas, and countries like Russia use that to manipulate the energy prices and use that for political reasons, so that the security of supply all of a sudden in 2021 became a lot less secure. Then also the traditional focus on security of supply it becomes more problematic in the light of accelerating climate change. We saw that in COP26, which was just a month ago, that there was the outcry and the public call to reduce the dependency on fossil fuels. But the focus on security of supply reinforces that need to focus on fossil fuels. And if that continues, we will never mitigate climate change, and the world may be approaching a catastrophe. Of course, it's not going to be soon, in decades to come, but the continuing expansion of fossil fuels is the concern, and a growing concern. Also, another note that explains the concern about the focus on security of supply is that price fluctuations for fossil fuels, particularly for gas during this year and in different time for oil, are frequent. They happen here and there, now and then. So the limitation of existing models, and again, please forgive me that this part of my presentation is very brief, but there are plenty of energy security models can be identified in the literature. The existing limitation is their ongoing reliance on fossil fuels. And that presents the need to eliminate, ideally eliminate, or at least mitigate, reduce this dependency on fossil fuels in the near future. And that, in turn, presents the need for a new novel energy security model, focusing on something else rather than security of supply. And speaking of a novel energy security concept, the starting point is to identify what theory it can draw on. And the theory is very straightforward, something that we all know, and that is the concept of sustainable development, meeting the needs of the present without compromising the needs of the future. Going back for a moment to security of supply as the current energy security concept, prevailing concept. If you ask that question, what is the concept underpinning that approach? And it's not totally clear what is the theoretical concept, because it focuses on some physical availability of resources at hopefully affordable prices. But that, as we know, can vanish very quickly. So the theory that underpins the novel energy security concept is the the concept of sustainable development. And now I'm coming to the core of the concept. And the idea is that for the focus on renewables, again, there is something, I'm saying something that we all know. And this idea will work very well when there will be a minimal dependency on fossil fuel. The question, of course, how could that be achieved? And that could be achieved by taking together three elements that you see on this slide. One is the focus on ever-increasing utilization of renewables, and at the same time, that needs to be accompanied by the corresponding decrease in fossil fuels utilization, and complemented by resource use efficiency. All three items that are underlined here at the bottom of the slide, we all know very well. But as of today, they are disjointed. They are not interlinked in one particular concept that would form the basis for policy and governance. So the key thing here is to integrate all three and use them at the same time. It's utilization of renewables accompanied by the corresponding decrease. In other words, that if utilization of renewables increases by 1 percentage point, then the decrease in fossil fuels utilization needs to decrease by at least 1 percentage point, ideally for the in the larger proportion. But that's the meaning of the corresponding decrease. And that will reduce the dependency on fossil fuels over time. Of course, it's not going to be in 1 or 2 years. It will take years. So just a couple more slides, kind of to illustrate the same thing. So we see the same terminology here, the same three things: ever increasing utilization of renewables, corresponding decrease in the utilization of fossil fuels, and resource efficiency. Down at the bottom of this slide, you see my name and the name of my co-author, and there are references at the end, and I'm drawing on the book that we wrote with my co-author on energy security, which could be easily found on the internet and found as the publication. Let me go back. And again, the same three elements are emphasized on this slide, linked by the lines showing their interlinked nature, and that they are should be taken all together. Now, a word about the energy security and how it will impact the nation's energy mix. The proportion of clean energy needs to continuously increase, accompanied by the corresponding decrease in the use of fossil fuels. When we look at some economies, particularly resource-rich economies, such as Russia or Kazakhstan, as you know, is rich in oil and coal, we can see that the proportion of the clean energy remains very, very small. We are talking about 2%, 3%, and sometimes even in some years, this proportion even decreases, which is exactly the point that in some years, when the demand for energy increases, the proportion of the clean energy, in fact, drops. And that we also see in other economies in the recent time when the acute phase of the pandemic was over and the economies were recovering quite fast. The demand for energy increased rapidly. And this demand usually is met by fossil fuels rather than renewables. So, but the most apparent problem with not increasing proportion of clean energy is can be observed by looking at resource-rich economies. they just got stuck with the fossil fuels for years ahead. Then speaking about the implications for policy and governance, the public acceptance for renewables is growing. We can observe that across the globe, and in fact, this conference is the great confirmation that the focus on renewables is growing, and the focus becomes more and more pronounced. But that is not enough. Again, I'm drawing to the presentations that I have seen together with you yesterday, and there were quite a few presentations about Italy and its progress with renewables, which is great. And Italy apparently is ahead of many other nations. But we also heard that in Italy, there are quite a few hurdles, impediments, when the projects focusing on renewables are not approved. They get stuck in bureaucracy, the procedures are not established. There is vagueness regarding what needs to be approved, how it needs to be approved, what criteria should be used. So there is no paradigm yet. There is no broad acceptance of the need for renewables in society yet, but it's growing. It needs to transform into a paradigm, the sooner the better. However, policy at the national level or regional level is not going to be enough, because policy needs to be supported by governance mechanism. And again, yesterday we in the presentations we have seen very many useful governance mechanisms. For example, I've seen presentations about carbon pricing, so which is one of the mechanisms. But and there are quite a few others, and they need to be interlinked. Right now, again, the problem with many of these tools, mechanisms, instruments is that they are viewed by governments and society in general as disjointed. The focus is at times on one thing, then at other time on the other thing, but how they are linked and whether they all together link to a set policy is often unclear. And in fact, these links most often are missing. So the policy paradigm needs to be supported by the range of governance mechanisms. And the same applies to resource use efficiency. My focus is mostly here on the energy itself, so focusing on renewables, but the same notion applies to resource use efficiency, which also needs a range of governance arrangements. Then the link between energy security and net zero. Net zero, in my view, should be viewed as a moving target, and meeting net zero as a goal from that perspective becomes very difficult. Why is it a moving target? It is a moving target because economies often present requirements for more energy. Again, we have seen that in 2021, when the acute phase of the pandemic was over. In fact, now we are approaching another acute phase of the pandemic with probably the downturn in the economies. And after that, it is likely to be the same thing again, that the requirements for more energy will be presented by the economies. And the question is how that increased demand for energy can be met by the economies. And the answer to that is that it quickly, within months, it can be met by fossil fuels, not by renewables. Why so? It is so because the financing for fossil fuels is easily available. Think about this. Is there a lack of investors in oil and gas? No, there are plenty, because everybody knows that this is the lucrative business and they expect good profits. Are there plenty of investors for renewables in the renewable energy? Not always, because the investment may be high, the governance structures are not well established, compromising the profits from renewables. So finding investors for renewables is a lot more difficult than finding investors in oil and gas. And another problem is that the last note on this slide is that when the volume of energy, the energy production needs to be increased quickly, like it was in 2021, it can be easily done by fossil fuels, but not by renewables. Renewables have clear limitations in terms of the output, and overall the output is smaller compared to fossil fuels. For fossil fuels, facilities are all there. They are all in place, and they have been there for decades, but not for renewables. So going back to net zero, so when the economy presents the demand for more energy, that as of today, that means that most likely this demand will be met by the larger use of fossil fuels, which compromises the target of net zero. So focusing on net zero and arguing that it will automatically bring us to renewables and will decrease the use of fossil fuels is, in my view, a misleading idea. Then the conclusive slide. Energy security should be viewed as a long-term process, meaning that the focus on renewables, of course, is the right goal, but the proportion of renewables in a nation's energy mix cannot be increased overnight. It will take years. So increasing the proportion of renewables and decreasing the corresponding proportion of the use of fossil fuels. So the public acceptance of renewables is growing fast, which is really a good thing. But it is likely that policy decisions in favor of renewables will be there in many nations. And of course, events like COP26 trigger additional policy decisions. So that is the additional benefit of those events, which is good. But
2 more minutes maybe to leave a little bit for discussion also, Mr. Moravian.
Okay, I'm finishing up. Yeah, so the policy decisions need to be supported by the governance structures. And at the end, I want to just show you that first item on that slide, and that is the book that I referred to earlier. So it's an edited volume on energy security, and the concept of energy security that I showed in part presented in that book, and other useful chapters can be found there. And that completes my presentation. Thank you very much.
Thank you very much. Now I would like to open the time for the decision. So we have also 3 attendees with us. You can also write questions on chat, or otherwise you can also ask or comment. Any comments, questions? No, okay. So
I have one comment / question if there are no other questions from attendees. Thank you for the presentation. I was curious about your point on supply being too much emphasized in traditional energy security models, which you said are sort of derived from fossil fuel use. I was wondering, isn't thinking about supply constraints equally, if not more important, when a large share of electricity is coming from potentially intermittent renewables? I mean, we know at the global level that electricity needs can be supplied with renewables to a large degree, but I think individual countries are going to be thinking a lot about supply in the context of energy security. So I was curious about your views there.
Are you talking about constraints to supply in terms of fossil fuels or renewables?
Renewables. So thinking about moving closer to the net zero energy goal.
Yeah, but the increase in the proportion of renewables inevitably will be gradual. So we are talking about the increases by a few, perhaps, percentage points every year. So obviously the increase in the proportion of the use of renewables depends on the investment and how quickly the facilities are built. So it will be a gradual increase. So in some countries that do not have enough investment, do not have enough climate conditions for wind energy or solar energy, that proportion of renewables will be growing very slowly. Yeah, I agree. There is some natural constraint there.
Yeah. So maybe I would also a little bit comment on this, because to me also it seems that like renewables are somehow in conflict with energy security, at least that if we see the situation now. Probably when we look at the supply side, it's not only the production of renewables that is really important, but probably also storage is needed to overcome somehow the volatility of renewables. So this should also be addressed, I think, in this concept of energy security. And in fact, I think you are talking about energy security now about green energy security, really, or sustainable energy security. So maybe this could be another term, yeah, or an improved term for energy security. Yeah. Okay, so because we spent all our time for the first presenter, maybe we have some time in the end. Thank you very much for these very interesting ideas and presentation. And we are moving now to Dr. Magdalena Clemun, who is assistant professor at the Hong Kong University of Science and Technology, and also postdoctoral associate in the Institute for Data Systems and Society at MIT. She also has a very rich publication record already, a lot of journal papers, and we are going to listen to the presentation on the evaluating the effect of energy technology choices on linkages between sustainable development goals. So please take your time for presentation. The floor is yours.
Thank you for the introduction. So I'm going to talk today about some recent work on evaluating the effect of energy technology choices on linkages between different sustainable development goals. And this is joint work with Sanna Oyampere, she's at Oxford, and Amy Schweikert, who is at the Colorado School of Mines. And I'd like to begin with a bird's eye view of this talk and overview. So it is well known that the Sustainable Development Goals are not independent. On the contrary, they're strongly interrelated because developments such as infrastructure expansion, for instance, transmission networks, as well as economic development more broadly, affect all kinds of dimensions of human development. And so that's obviously important to think about these linkages. And for this reason, there's been a wealth of literature characterizing these interdependencies between different SDGs over, I would say, the past 5 years. But one aspect that has perhaps received a little bit less attention is how these linkages depend on choices of technologies. So when we look at SDG 7, there's sort of 2 keywords there, affordable and clean energy, and we can envision a couple of technologies that meet these criteria, but these technologies may individually consist of different components and services and industries, which may have other effects on non-energy SDGs. And so in this work, we explored this question a bit further which is how does the nature of SDG linkages or interdependencies depend on technology choices and also deployment strategies, so whether these technologies are manufactured locally or predominantly imported. But before I go into the specifics, I wanted to briefly touch on the general framework behind SDGs. So these 17 SDGs and 169 associated targets, of course, cover many different aspects of human development. But when we think about specific investment strategies or policies, these rarely, I would say never, tackle all of these SDGs. That would be amazing. But by nature of being rooted in certain sectors, such as energy, policies typically focus on one primary SDG, one primary investment goal. So when we think about feed-in tariffs to promote clean electricity expansion and so on and so forth, they focus on one SDG. So that raises the question, what are potential linkages with other SDGs? And that question is, I would argue, gaining in importance for a couple of reasons. We are in a global pandemic and therefore concerned not only with sustainable energy and reducing greenhouse gas emissions, but also with economic recovery. So there you already have more than 3 SDGs. And then there are also practical on-the-ground financing reasons from a development perspective. So there are now funding tools that are specifically dedicated towards what people call multi-dimensional projects that focus on multiple SDGs at the same time, with the goal to reduce competition for development funds, to avoid duplications of different development programs, and also to increase the coordination between institutions in countries that are perhaps fighting for resources dedicated to different SDGs. And research can help with regards to making these tools more effective in terms of allowing to prioritize policies with greater potential to deliver progress on multiple sustainability fronts rather than just one or two. And like I mentioned in the beginning, there's been a lot of previous work on this topic of linkages, specifically focusing on SDG 7, so clean and affordable energy. Research has shown that it is one of the most central, so interconnected goals within the 17 SDGs. And these linkages for SDG 7 are predominantly synergies. So they predominantly make it easier to also make progress towards non-energy SDGs, but there are also trade-offs. So just some examples. Improving access to clean and affordable energy will often also make it easier to power medical facilities, thereby supporting progress towards SDG 3, good health and well-being. And it will also make it easier to power food systems as well as water treatment systems, thereby contributing to progress towards SDG 2 and SDG 6. And trade-offs can arise from well-known effects of fossil fuel usage on human health through air pollution, as well as on ecosystems, providing food and water security. But despite probably over 90% of linkages at this point having been analyzed, their dependence on specific technology choices remains somewhat understudied. And there could be differences in the nature of linkages, so which SDGs are connected and how strong these linkages are, depending on the specific physical components as well as services required for individual technologies. And I'm interested in this question, of course, looking at the energy sector, because that's the area that I work in, but it is a broader question. We could think of examples of technology choices to support a primary investment goal. So for instance, one might want to expand the use of artificial intelligence in what people call smart farming to make progress towards SDG 2, and then wonder about effects on other SDGs. Or one may consider expanding the use of three-dimensional printing to reduce material consumption and waste in pursuit of SDG 12, sustainable and responsible consumption. So in all these cases, the question, the main underlying question is, what happens to other SDGs if you choose a particular technology to make progress towards a primary investment goal? So how does the nature of potential linkages between SDG 7, here I focus on SDG 7, and non-energy SDGs depend on the choice of energy technology? And then how useful is the SDG indicator framework, so this set of 231 indicators to analyze SDG linkages? And in today's talk, I focus on a subset of these indicators and SDGs, looking at SDG 6 as a sort of representative SDG for environmental impacts, and at SDG 8 and 9 as two representative goals for economic impacts, and using a few example technologies to sort of test a blueprint for screening different technologies for potential interactions across SDGs. So that's perhaps a similarity to the previous speaker. This talk is conceptual in the sense that the framework is really the meat and not so much the quantitative results, although I am going to present a few snapshots of those quantitative results as well. And so the way we conceptualize linkages between sustainable development goals here is through technology components, industries, and SDG indicators. So essentially we break down energy technologies in their different hardware components and different installation steps or services, and then use this bottom-up view of different technologies to list all manufacturing, mining industries, engineering services required to produce these technologies and make them functional at the point of use. And then we use a combination of data collection directly using data for SDG indicators to the extent available, and a review of the broader literature on associations between technology manufacturing and industry water usage, and other indicators related to the SDGs that we examine, to determine whether a condition for a linkage to be considered possible is present. And that condition is that there's at least one peer-reviewed source confirming that there has been a relationship in the past, or that physically that relationship is very likely. And so this is how we connect technology components, industries, and SDGs. And conceptually, we can think of this as a tripartite unweighted network where the technology components, industries, and SDG indicators are the nodes, and they are connected if technology components require certain industries and services to be manufactured and delivered, and if there are proven associations between industries and sustainable development indicators. And so in that sense, a linkage between different SDGs emerges if a technology requiring certain industries influencing certain indicators is used. So this is the conceptual backbone. So just to give you a little bit of a sense of how this works in practice, so for photovoltaics, we have components such as the module, the inverter, and then we have soft components, so services that are also required, such as system design and mechanical, electrical installation, and for clean cook stoves, which we include here to also have a sort of simpler and heat supplying technology in our set. We have components such as the stainless steel body, the burning chamber, and so on and so forth. And then for industries, we use the North American Industry Classification Code at the 6-digit level. So we go all the way from mining to manufacturing to different services registered under this code. And so after making the decision whether the literature indicates potential for a link between an indicator and an SDG, we define two metrics to essentially summarize how likely an industry influences a particular indicator. And based on the different indicators, so each SDG has between 5 and 16 indicators associated with it, we also sum up these results across all indicators associated with an SDG. So what you see here in the numerator is the number of connections between industries and indicators that are considered as possible. And then we divide that by the total number of connections between all technology industries required to manufacture a technology's components and a particular indicator. And then, like I said, sum it up across all indicators for an SDG. And before I talk a little bit about the quantitative results, we consider two scenarios as boundary cases. So most real-world energy projects will involve a combination of locally manufactured or imported components. Since we consider one scenario where all components are manufactured locally and all services are purchased locally, and another scenario where everything is imported, we can assume that real-world energy projects are sort of covered by this range of results because they will tend to fall in between or closer to one or the other end of the spectrum. All right, so this is the technology industry network for wind turbines. Just to give you an example, I'm not actually showing the connections to make it easier, make the list easier to grasp quickly. So you see all kinds of components and then all kinds of industries. Overall, we do see differences in these technology industry networks. So both in terms of how many hardware components versus different services are needed to manufacture and deploy a technology. And then also in how these industries and services are distributed across different types. So is it mining, construction, transportation and warehousing, professional services, and so on and so forth. And these differences in the technology industry networks then also translate into differences between technologies in terms of their potential to create or enhance co-benefits and trade-offs. So here I'm showing the technology indicator densities for all technologies, photovoltaic systems in yellow, wind in blue, nuclear in black, and clean cook stoves in red. SDG 6 on the left, SDG 8 in the middle, and SDG 9 on the red. And you can see some similarities, but also differences. So I'm going to talk a little bit more about where these come from. If the density is positive, it essentially means that there is a potential for a co-benefit between SDG 7, clean and affordable energy, and another SDG. And when the density is negative, there's a potential for a trade-off between SDG 7 and another SDG. So here for SDG 6, clean water and sanitation, we see that both the score for solar photovoltaics and nuclear fission is slightly higher. That has to do with a stronger presence of water efficient services in their technology industry network relative to the less water efficient manufacturing industries. So if we consider a marginal unit of these technologies being added to countries with a globally averaged water use efficiency, then a technology with a higher presence of water efficient service industries can promote positive change or has a higher potential to achieve positive change as opposed to other technologies. And then for SDG 8, we see one reason of the differences between the technologies here is the stronger presence of industries with a potential for informal employment in the technology component industry network of solar photovoltaics. Here I should mention that informal employment can be both positive and negative. So for a developing economy, this may be initially something desirable, but this is one of the indicators of which there are actually multiple, where there is some level of interpretation required of whether this change is something desirable or not. So here we included it in the positive density, assuming that we're representing developing countries. And we also have the data from IRENA for the jobs creation potential of renewables in the informal economy. And then for SDG 9, industry, innovation, and infrastructure, we see solar photovoltaic scoring slightly higher, which has to do with the stronger presence of high and medium tech industries in the network of photovoltaics. So these are, for instance, building inspection services, engineering services, architectural services, and the indicator responsible for this result is 9B1, the proportion of medium and high-tech industry value. So you can see that there's a whole layer to these results. There are different indicators within each SDG, and these are linked to the different components and service industries required for a technology. This was the import scenario. So here we're assuming that all technologies and services, all components are sourced from abroad, not within a country. Moving on to the local manufacturing scenario, so the other boundary case, now we're assuming that all components are sourced locally. Interestingly, that leads to actually quite similar co-benefit results across technologies. Thinking about it a little bit more, it makes sense though, because all technology industries contribute to industrial water use, potentially water stress, contribute to unemployment reduction, to growth in GDP, and so on and so forth. So when we assume that all manufacturing occurs locally, there are actually more similarities across technologies. Some of the trade-offs are due to effects such as increases in the material footprint for SDG 8, for instance, and some industries showing elevated risks for occupational injuries, as well as some industries showing higher CO2 intensity per unit of value added, which affects SDG 9. And then cook stoves here tend to show the highest negative density score because their overall component industry network is relatively small. It's a simpler technology, and therefore the few industries with elevated occupational injury as well as child labor risks, which are both things that are captured in the SDGs, both 8 and 9, carry a larger weight relative to all the other industries in this network. So in summary, the screening of different energy technologies based on the impacts of their services and industries has revealed differences across technologies' potential to either enhance or induce co-benefits and trade-offs between different SDGs. And interestingly, as I showed by starting with the component import scenario we consider here, these differences are driven by the deployment phase, so meaning services, as much as by component hardware manufacturing. So it is important when we want to understand the nature of these linkages a bit more to consider both the physical components of different technologies as well as how they differ in terms of the services that they require. And our analysis has pointed to some of the origins of these differences. So is there a stronger presence of high versus medium and low tech industries in a technologies network? Is there a stronger presence of service industries overall versus mining and manufacturing industries? Because these industries affect other SDGs such as clean water, as well as innovation and so on and so forth in different ways. And as the last point, I also wanted to highlight that we noticed that the nature of these linkages, so any conclusions that you draw for SDG 7 connected to another SDG, can often depend on which indicators are emphasized within an SDG. So like I said, there are between 5 and maybe 16 indicators per SDG, and these capture very different aspects of, for instance, economic development. For SDG 8, you have metrics such as occupational injury risks, child labor risks, and more standard growth metrics such as GDP growth, employment, freight volumes, and so on and so forth. And not all technologies perform, of course, the same across these different indicators. So SDG linkage conclusions may depend on which part of an SDG in terms of indicators is actually emphasized. And with that, I look forward to any comments, questions, or feedback. Thank you.
Thank you very much for this very interesting presentation. And I would open the floor again for the discussion, comments. Also, I invite other attendees to discuss.
May I?
Yes, please.
Okay. Thank you for this interesting presentation. My question is, are there implications for policy or governance from your study, or you are not looking at these at this point?
I think probably the strongest implication is the importance of data collections to track all the indicators that affect the density score that I presented here at the local level. So some of the conclusions I presented are hold for the global average because, for instance, the water use efficiency of service industries is so much greater than the average water use efficiency of most countries currently. So then you don't need necessarily a regional analysis to confirm whether or not there is potential to induce positive change. But there are other cases that are much more regional dependent, and there's the data to evaluate these linkages is simply not available. So in some sense, and thank you for the question, I'm actually thinking of this work as a way to guide government analysts towards the metrics that are particularly important to understand certain linkages depending on which SDG is the primary investment goal. Of course, this is just the starting point because we're only looking at SDG 7 and we're only looking at a subset of other SDGs and at a subset of energy technologies. But this is sort of the grand plan, if you wish, if we were to continue this work, which I hope to do.
Thank you.
Thank you. So as we can see, really, these linkages are really could be very different in different countries, depending also on the weights we give to different indicators. Mm-hmm. So maybe that would be also the direction for further research. So mm-hmm. maybe whether to have equal weights for all the indicators or whether to, prioritize some indicators and so on. And mm-hmm. Also how much this could be country specific. Yeah, that would be very interesting, I think. And also maybe the one direction for further research may also be to look at other goals. Let's say sustainable cities. I think it's SDG 11 or 12, responsible consumption and production, or maybe 13, climate action. Mm-hmm. So that I think are also interesting goals, really. And my question would also be, how did you perform the literature review? You mentioned that you looked at the impacts mm-hmm. Of technologies based on the literature review. Mm-hmm. Yeah, so how did you perform that literature review? Mm-hmm. Did you select journal articles only, or I mean, in what way?
Yeah, so we predominantly focus on the peer-reviewed literature, but it's not only journal articles. We also consider technical reports published by international organizations that work on energy and sustainability as peer-reviewed, because they typically are. And then the way we approach the literature review is to use the list of technology components and industries and services to generate a set of keywords, which we then typed into search engines such as Google Scholar, and looked for confirmations of the potential for these linkages existing in the respective journal papers that were the result of our searches.
Okay. Do we have any other questions, comments? So as already said, some policy conclusions maybe would be very useful, yeah. So to think about it for the future work as well. So if not, thank you for your presentation, and we are moving to our fourth presenter. We have Dr. Nala Paneni Manoy Kumar. I hope I pronounced this correctly.
Yes, you pronounce it correctly.
Yeah, so thank you. And Dr. Kumar is now postdoctoral research fellow at the City University of Hong Kong. And he also has a very rich publication records, over 150 journals and conference, so papers in journals and conference papers. And we are looking forward to a very interesting presentation with some new ideas. So this is blockchain-enabled dynamic grape voltaic farms for selected wine risk regions on a global level and the potential opportunities for symbiotic industrial networks. Please.
Yeah. Thank you. Yeah. Thank you, Nevenka, for introducing me. So I'll share my screen and take over for the presentation. Can you all see my screen, right?
Yes.
Yeah. So as Nevenka mentioned that it is an interesting topic, a combination of different technologies and different research fields, and even different engineering and management branches together are there in this topic. So without wasting much time, I'll give you a brief idea of what we have done and what we are up to in this topic. So today I'm here to present blockchain-enabled dynamic grape voltaic farms for a selected wine risk region and the potential opportunities for symbiotic industrial networks. So the title itself is suggesting that we are mainly concentrating on a wine risk region. So that means wherever there are climate risks associated with grape cultivation, we are trying to address that using a systems level approach by proposing a novel system. So now if you see the background, there are a lot of winemakers around the world, and here is the map showing the wine risk index, considering the frost index, one of the climate resilient factor. So because of this climate risk, winemakers are losing billions of dollars all over the world. So that may be either Europe or America or even in India or even in some of the African nations or even in Australia. So it doesn't matter whatever may be the region, there are different types of natural disasters that due to climate change issues. So all were affecting more or less in similar ways, and winemakers are losing a lot of money. So here we try to address this sort of issue and try to develop a climate resilient grape cultivation method. So for taking a representative case, what we did is we try to consider the most grape grown city in India. So I'm also being from India, and Nasik is my own state where I live, and my father also do agriculture. But my father does agriculture in chili and cotton, but these grape farms are very close by to our agricultural land. So I have chosen this Nasik and Sangli regions in India as a case study for development. And then we did some literature review and quantifying the climate resilient issues on this region. So what we mainly observed is these regions will have a lot of rainfall and hail. So due to which the grape crop is damaged. So once the grape crop is damaged, more or less the grapes are unsuitable for wine production, are also not suitable for food productions or other food derived products. So mostly in India, we grow wine grapes as well as table grapes. Both we grow it. And wine grapes are more grown in Nasik region, and then table and other kind of grapes are grown in Sangli region. So what we mainly observed is we interviewed with the farmers growing these grapes, and we asked their conventional climate resilient practices, what they do. So they're mainly practicing rain heat production units, and also in terms of pest or something, they might be using nets and all. So we thought, like, instead of using rain heat productions, instead of this pest nets, why not we go for a new technology that is readily available concept as agrivoltaic systems. So agrivoltaic system is nothing but we use the same land for producing agriculture as well as the solar energy electricity. So the figure is shown on the left hand side here. So this is an agrivoltaic concept. What it mainly does is this is inspired based on the land use conflicts between agriculture and solar electricity productions. So on the record, 1 megawatt of solar photovoltaic plant will require at least 1.9 hectares of land. So due to which there is a growing land use conflicts between solar industry and agriculture. So we thought of addressing this land use concept, land mitigation concept, and also at the same time thought of using the solar panels as a protective shield against this climate resilient, either if of rain or hailstorm or heavy windstorms. So all such things can be mitigated by using this agrivoltaic systems. But however, the conventional agrivoltaic systems might not be a good solution for it. So what we did is we try to convert this conventional agrivoltaic system to a dynamic one. So what does this dynamic agrivoltaic system does is the solar panels, what we placed here, will tilt accordingly in this direction. So this tilting position is again managed based on the climate disaster activity. Let's say if it is a rain, based on the rain direction, the panel will be tilted. If there is any sandstones, accordingly, the panel will be like coming into the standby position, and it will cover the grape crop completely. So that sort of motivation we had it, and we further went in developing this concept. But when we thought of developing that concept, so it's like we are integrating both grape farmer and solar PV operator together. When we integrate both this solar operator as well as the grape farmer, there might be a conflict. So it becomes like a management issue. Why solar PV operator has to support the grape cultivation, because during any event of climate disaster, there might be a possible effects with the solar panel, or else if solar panels are tilted to other directions, based on the tilt angle, solar panel production might be reduced. So it becomes a conflict situations. But we wanted to develop this concept so that both grape producer as well as PV operator will become profitable. So how to establish that synergy is a big question for us. So when we thought of this from a realistic point of view, after interviewing with few of the farmers, whether they will agree with this concept or not. So what we mainly found is both are not compromising with their own with their own profits and their production limits. So what we found is we mainly found that there are three issues that are possible. The three issues are trust, transparency, and traceability. So why I mainly consider the trust and transparency issues is both stakeholders has to be transparent to each other in terms of their climate disasters. And also they should have a trust that one will support other in the event of climate risk, or the other will support in the event of climate risk. Then the traceability concept we have added here. The main reason for it is most of the grapes grown in India are exported to European countries or some other Middle East countries. So the European Union has a special regulation on grapes grown in India. So that regulation is They don't want it to have a pesticide content, and it should be more or less a low carbon grape. So that is the reason we wanted to create a traceability reports for this grape cultivation. So we combined this as a triple T issue, starting from a system design point of view or from a supply chain point of view. So now we wanted to address this three T's, and with the new system what we developed here. So for this reason, we have two overarching goals. The goals are to develop a novel distributed ledger technology use case, that is a blockchain food energy water smart contract. So it's called as a BlockFew, and the terminology what we used is the SP or SS, because we wanted to link this under circular economic concepts. So under circular economy concept, there is a business model called shared economy or a shared platforms or a shared services. So shared services are nothing but two business partners are coming together to start a business activity. So here also a food production as well as energy production are coming together to start a business activity in same land. That means they are using a same land surface for going this business activity. That's the reason we link this under shared business practice. Then the other thing is to examine this BlockFew smart contract, whether it is resilient or not, whether we have any sustainability benefits or not, without compromising this co-production benefits. So we wanted to evaluate this. So for this reason, we have opted for a methodology that is a replicate approach, which is a mixed methods combining resilience, sustainability, and also the techno-economics. So together we call it as a replica method. And the methods are not individually developed by me, because these methods are already existed. For example, the resilience performance method is taken by Igor Linkoval. It's a paper published in Nature Climate Change. And also the conceptualization of this resilience indicators were given in one of the paper in scientific reports in Nature. And then the rest two methods are well known to most of us, life cycle assessments and TEA. So what I did is I tried to combine these three methods and formulate a new mixed methods approach and applied it in the new system I developed it here. So now the designed blockchain food energy water smart contract based network will appear like this. So here, if you see on the left hand side, here I have this NDLT strategy. The NDLT strategy is given here, the architecture of it. So this architecture mainly consists of various layers, because this is purely a software architecture, and it has a sensor layer, connectivity layer, data storage layer, analytics layer, application layer, and stakeholder layer. So each layer has its own functions, and they are integrated to a real world as well as a virtual world. So in the sensor layer, what happens is we equip the system with all sorts of sensors that are possible to recognize any climate disaster issues. Say, for example, rain, pest, or heavy winds, or hailstorms, or like too much sun. So all these things can be sensed by the sensor layer. And then once the data is sensed by the sensors layer, it will be sent to the cloud storage through a connectivity layer where we have a gateway and wireless connectivity. It's like a wide and Wi-Fi networks. So using that, the entire information will be on cloud storage. So once we have the data in a cloud storage, what we do is we send this data to a blockchain ledger. So in the blockchain ledger, what happens is all the data will be stored as per the stakeholder specific. And then here we have a smart contract. So here we write a smart contract. What does this smart contract does is, whatever problems we discussed in the previous slide, that is the triple T issues, those issues were articulated in the smart contracts. That means in the event of a disruption, both stakeholders should support each other so that they can overcome this climate resilient issues. So that means in the event of too much sun, the solar panel has to provide shadow to the grape farmer so that the aromatic flavor of the grapes can be maintained. Or in the event of rain, based on its direction, solar panel has to be tilted, or has to cover the grape plant completely. So such contracts are already written in the smart contracts, and accordingly, the data is visible to the front end user. So the front end users are both grape farmer and solar PV operator. So this is what the architecture, what you have given on the left hand side. Now, if you see the typical conceptual flow of this marketplace is given on the right hand side. So here you have a photovoltaic operator and grape farmer. So their smart contracts and mutual cooperation are given here. So apart from this shared resilience aspects, we are also given two other indicators that are mainly related to water and energy, because they are sharing the land, but we wanted to share the energy also, because we wanted to produce a low carbon grapes. That means we wanted to use the producer solar electricity for irrigation and other activities in the grape for the grape farmer. So that's the reason the solar PV operator has to share its energy. And then we even have rainwater harvesting support systems and water sharing for cleaning and resilience support. So the reason for water sharing we have given is solar panels have to be cleaned for every 1 week or 2 weeks onwards because of the dust deposition on the panels. So here, if you deposit dust on the panel, the efficiency of the solar panel will reduce. So that means now the solar PV operator can't compromise for its production levels. So that's the reason the grape farmer has to support cleaning water to the photovoltaic operator. So, but it becomes like too much of water usage for photovoltaic operator as well as too much of water usage for grape farmer. So what we come up is, in the system itself, we designed a rainwater harvesting facility with the solar panel itself. And then we wanted to use rainwater harvesting system for a rain washing of the solar panels first, and then that water is again collected and gone to the drip irrigation system, so that the water is fully conserved here itself. At the same time, the energy is shared between two stakeholders and the rest is given to the marketplace, that is the grid. At the same time, the grape farmer will send it to the grapes to the marketplace. So this is the overall architecture we have developed. And then the system description is like this. So once we have the digital system ready, we wanted to implement this on a physical level in a real farm. So if I wanted to implement this on a real farm, first I need to have a system design ready. So what I did is I have considered a 1 hectare of plot. So if you see on this green one, I have taken 1 hectare of plot. So the plot size is considered as 100 m by 100 into 100 m. So in this, I designed this entire dynamic grape voltaic farm, considering the solar plant installation guidelines as well as the grape farming guidelines given by Food and Agriculture Organization as well as the National Grape Research Center in India. So what we did is we found that row to row spacing for the grape plant is 3.6 meters. At the same time, distance between two white trellis is 5.48 meters, and row to row spacing between the photovoltaic arrays is 5.1. The reason for having a 5.1 meter space between photovoltaic arrays is the shadow of one photovoltaic array should not fall on another photovoltaic array, so that the efficiency or the final electricity yields from the photovoltaic plant will not reduce. So that's the reason we have this 5.1 meter distance. So that way we designed the entire dynamic grape voltaic system. So what we found is 1 hectare of plot can have at least 1458 vigorous vine varieties and 5040 solar photovoltaic modules, each of 100 watts here. And the typical structure of this, each one would look like this. The top is a solar panel, and these are the white trellis, and these are the grape plants. So, and the line you see is a drip line, and the water coming from the, whenever rain is falling, the water will be collected here and then it is gone. So the clear description of water flows is given here. If at all rain falls, so now the rain falling on the panel and it is collected through these chambers and it is gone to the pipelines and it comes to the filter, because the dust deposition will be there on the solar panel. So we have to filter it. Once we filter it, it will go to the main water storage tank, and from there it will go to the grape plants as well as solar panel cleaning in the event of no rain. If at all rain is there, it will come as a rain washing itself. And if there is an excess water, it will go to the groundwater. It's like, we discharge to the groundwater. If there is no sufficient rain, we get the water from the ground level. So, and while modeling this grape cultivation, we considered evapotranspiration coefficients in the given region. And now the results are here. So we have two different set of results for in terms of crop and energy production here. So we compared the grape production results with business as usual scenario also here. So what we found is in the business as usual scenario, more or less the table grape and wine grape productions are similar. We have given that in terms of tons per hectare. Whereas in the case of dynamic grape voltaic farms, the produced grapes, the table grape variety is higher than the wine grape. It's because of the shade tolerant and other aspects we found it. So the yields table grape is 45 tons per hectare and wine grape is 35 tons per hectare. And the average is like the electricity we produced is 911 megawatt hours of solar energy per year. And the monthly energy distributions, what we produced are given here. So we have even accounted for direct electricity that is coming at the PV panel terminal first, and also at the distribution side after considering the whole system losses. And then the annual solar radiation incident on the grape voltaic farm is also given here. And now we did the economic assessment for the system. So what we found is we found that the cost of electricity produced from this grape voltaic system is varied between 10 rupees to 25 rupees. And then we even applied different sensitive analysis parameters. These parameters are degradation coefficients. So the main reason we applied as a degradation coefficients as well as discount rates, because not all plants can be installed at a DR of 5% or 1.2% or 25%, because different regions in India have different discount rates. So we try to conduct this scenario, and what we observed is the price can be of somewhere varied between 5 rupees to 10 rupees if you opt for different discount rates. At the same time, we even estimated the table grape selling price. So the table grape selling price is also varied based on for different CDRs. So here the CDR is nothing but crop degradation rate, because this grape crop and solar plant, both lifetime is more or less 20 to 25 years. And over the period of this 25 years, every year there will be a decline in the crop production rates or energy production rates. So that's the reason here the crop degradation rate is varied between 0 to 20%. And what we observed is the 1 ton table grape price could vary between somewhere between 35,000 to 55,000 rupees. And similar way we performed for the wine grape selling price also. And now once we found the selling prices and also unit prices for both electricity and grapes, we applied this in the blockchain payment gateway. So where we try to have a P2P trading methodology. It's like we are bringing the consumer as well as the buyer and seller together on a digital network, on a blockchain network. So that is how here solar PV operator will have all its energy that is displayed in the front end of his database. Then whoever is needs, they can buy the power, either it is a grid or neighborhood farms or a neighborhood villages. So everyone, they can buy it directly. And the same way we have even for a grape trading also. And then the overall cost we found as the revenues or cash flows we observed is when compared to table grapes, the wine grape cash flows are higher. Also the electricity potential cash flows are much higher. And now we went one step ahead to see whether the system is sustainable or not. So in order to assess the sustainability aspects of the system, we considered life cycle assessment, and we used a SIMAPRO 8.52 version, and the database we used is the EcoInvent, and all the results are quantified taking a functional unit of 1 kilowatt of produced electricity for solar plant owner and 1 kg of table and wine grape produced for grape farmer. And the system boundary we consider is a gate to gate. So the reason for considering the gate to gate here is we just consider the farm site itself our system boundary, because the whole supply chain is we don't have any life cycle inventory data at this stage, but still we are collecting the data and we wanted to extend this work. So that's the reason we just considered with the gate-to-gate system boundary. And the environmental sustainability results indicate that the mitigated land footprint is 1.984 hectares per megawatt of our solar. And then the table grape in this shared business practice has a CO2 value of 0.11 kg of CO2 per 1 kg of table grape. At the same time, in the business as usual scenario, it is 0.21. So it's more or less we reduce the carbon content of 0.1 kg per 1 kg of grape. And similarly with wine grape also, we observed that 0.08 kg of CO2. And then we even have other normalized results for global warming and terrestrial ecotoxicity and water consumption. The main reason for considering these three parameters is in the grape cultivation, we might use some sort of materials, though it is organic content or something, but cow dung or some other materials we might be use it. So we don't want it to have any ecotoxicity. So we try to estimate that one. At the same time, water consumption, we have considered, though we have a rainwater harvesting system as well as the drip irrigation. The main reason for considering it is the solar panel cleaning, because solar panel cleaning consumes huge amount of water. So we wanted to see how our system is efficient in terms of water consumption. So we have considered these three parameters and we analyzed it. And after we see that, we try to explore various symbiotic energy industrial networks possible. So after our expert interview with different farmers or wine production or different grape derived food products productions in the local sites, what we observed is there are few farmers who are interested to produce resins in the farm itself. And also some vineyards have a small scale wine production in the farm itself. And then grape seeds and other pulp they're exporting to some other industries, especially the grape pulp is gone to pharma industries, and the seed oil also is given to other food processing or biodiesel production industries. So what we suggested is, why not we have a synergical industrial networks in neighboring locations itself. And then we explored all these possible industrial networks, especially wine production is possible on a massive scale if we have a proper water, electrification and all these things. And resin production is also possible because they need to get dry. So we even opted for solar-based drying also. And then the grape-derived food processing industries that can be possible in the local villages and the neighborhood regions. And grapeseed oil will not take much of machinery because we just need a crushing and processing and purification itself. So hardly with like, 3 or 4 machinery, they can just have this grapeseed oil production. And then the grape pulp processing and grape-derived pharma. Of course, the grape-derived pharma is not possible on the site itself because it has to be exported to pharmaceutical industries. So we try to find out that are there any local pharma industries, but we found that they're almost like 100 to 200 kilometers away. So we still need to quantify the supply chain or the logistical issues arrive there and see whether grape-derived pharmaceutical industries also can be possible or not in neighborhoods. Yeah. And then the summary is what we observed is, it is observed that by applying a blockchain could facilitate the shared circular business model and promote grape and energy trading. And also leveraging this model with existing GrapeNet is observed to be feasible. So why I wanted to apply this GrapeNet concept is, as of now, there is an export organization in India that is EPADA. So where they use the tool called GrapeNet. So this tool has been developed just because of the compliance issues that arise with the export quality of grapes with European Union. So right now they have different certification process. Each grape farmer has to take it. So we thought of integrating our blockchain-based network with the GrapeNet so that it becomes more traceable and more transparent. And overall, the TA and LCA results reveal that this dynamic grape voltaic farm is feasible, promoting low carbon grape production and scope for decarbonizing energy sector by obeying the land use norms. And the future works includes, we wanted to apply this, leverage the same system to different crops. And also we wanted to see how different solar cells can have enhanced energy yields or can we use any transparent or semi-transparent solar cells.
Just, yeah, we need to end if we want.
Yeah, it's almost done. It's almost done. 1 minute, it's almost done. And similarly, we wanted to explore symbiotic agriculture and electricity and industrial networks possible under different crops. And thank you. If you all have any questions, please feel to ask.
Yeah, so thank you very much. I have a question. So you were talking about a modeled farm. Are there any plans to implement this project in practice?
Yes, we are thinking to implement. Right now, we don't have much fund, but we are trying to apply. We wanted to apply, and we have interacted with a winemaking farm that is Sula company. I think you might be knowing Sula Wines in India. So they have huge wine farm also. So we approached them and they're quite interested. But
so
still
try
we
to
want
find the investors.
Yeah, we still wanted to take it to European Union because they have a lot of wine farming, right?
In my view, in Europe, it may conflict with some aesthetics,
Okay,
because of the farmlands and so on, the winelands, vineyards are very nice, and maybe it's also tourist regions, or in France, I think,
that is
around
true.
Bordeaux and so on. I don't know how much they would be willing to accept these projects. But one more question regarding the selling prices that you mentioned regarding electricity. So how do these prices compare with actual prices, real prices now? And have you calculated the rate of return on this investment?
Yeah, we calculated the rate of returns. The rate of returns are almost like 14 to 16 years. So it's because, we did
So this is the time and the rate of return itself. So lifespan is 14 to 16 years.
For solar photovoltaics, it is 25 years typically in India, even considering the degradation rates. The reason for this is, right now there is no proper regulation for agrivoltaic systems in India. So we are even approaching the legal bodies to set the solar electricity price produced by agrivoltaics. And this year, Indian government has launched a new feed-in tariff regulations for agrivoltaic systems, but still, those systems are interspace cultivation, because what the model we have shown is the overhead system, but the conventional system is the interspace cultivation. Whatever space left over between different solar panels, they are growing different agricultural foods. For that only, Indian government has released, and the unit price is somewhere between 6 to 8 rupees right now. But for this system, almost if you consider the degradation on all elements, the price itself is above 9. So, and the main reason for this is the additional infrastructure that is caused while building this system. So that's the reason the rate of returns are quite high. So I think we're still exploring the possibilities of reducing the material cost, or trying to share the resources equally between solar plant owner as well as the grape farmer owner, so that the crop prices can be altered. We are looking into such possibilities. Yeah.
Okay. So I don't know, do we have any quick question, because we are coming to the end of the session?
Sorry, I took a lot of time,
Yeah.
I have a quick question. It's quite broad. I was curious. So some of the techno-economic and life cycle analysis results could be generated, I guess, even without the blockchain part of your proposed technology. So what do you think?
True. Yeah, true. We can generate without the blockchain too.
Using blockchain for commercializing it, perhaps.
Yeah, the main reason is, as I mentioned earlier, these 3 issues, the triple T issues. Let's say now, if the solar panel is in a tilted position, always like if it is on close to the latitude angle of the location, solar plant owner can make more revenues because he gets more electricity. But now in the event of rain, the rain might be in a different direction. So that means the solar panel has to be tilted. Or in the event of, overhead rain, solar panel has to come to 0 degrees. So in that case, I'm not sure whether solar plant owner will compromise or not. He might say, I have more energy, right? And whenever there is no...
Basically optimizing the field for rain protection as opposed to optimizing it for energy yield.
Energy. So we call this 3 issues because blockchain has a potential to solve any of these three issues. So then we gone for, IoT based approach here. So we optimized every parameter based on the real-time data that is sensed based on different weather and environmental factors. Yeah.
Okay.
Interesting. Thank you.
So thank you very much. Thank you all the presenters for these very interesting topics and presentations. And I hope that you will stay at the conference also during the day, and hope to see you sometimes in person. Yeah, so maybe
sure.
other conferences of International Association as well. So have a good day and goodbye.
Thank you.
We are finishing the session.
Thank you.
Thank you.
Thank you.
Bye-bye. Yeah.